So the cabbage indicator lab is based on these anthocyanin compounds, and when they react with different amounts of H plus, they create compounds that have a slightly different chemical structure. Now these chemical structures bend on the d orbitals, which the electrons are in, and the different splitting between the d orbitals means there's different wavelengths that come off, and your eyes see those different wavelengths. And so when the d orbitals are split to a large degree, there's a lot more energy off, and you're going to see sort of the violet compounds. And when the d splitting, the electrons are jumping between the d orbitals is not so great, there'll be longer wavelengths, and you'll see more the red color. And so you'll see different degrees of different colors based on different amounts of H plus in the cyanin. So that's how colors work. They work between the electrons jumping between splitting d orbitals. And so what you're basically going to do is just extract them out of the cabbage just by boiling it for a certain amount of time, maybe 5 to 10 minutes. And then you can just grab a little bit of each and put them in test tubes like this, ready to test various compounds. So we're going to look at qualitative and quantitative. Obviously, quantitative is better. The numbers is always better. The language of science is math. So we prefer the quantitative rather than qualitative data. So first of all, just some qualitative. You just need to know that fruits, and this one's here's lemon juice, they give acidic compound, so that's on the red end. And then you have detergents on the basic end, soaps and detergents. This one's actually more like water. It was actually an empty bottle. I just put some water in there and hoping it would still have some base in there, but it's not really. It's kind of neutral, but that's fine. And so if you're at maybe the year 11 chemistry level, these first two are for you, and then the next one's a year 12. And so the first one is if you've got a monoprotic acid, it's strong. So you're going to see that the arrow is here. It's in one direction. And you're going to find the Kas are going to be large, greater than 1. That means it completely dissociates. And so the qualitative is just red. It doesn't tell you a lot. But if we go to quantitative, we can take a measurement with the pH meter that it's we can see it's around 0.3. And if you're in year 11, you learn to use the formula pH is negative of the hydrogen ion concentration. You can see the Ka is quite large, so it must be strong. So Ka just is an equation of products over reactants. You'll learn how to do the expression in year 11 properly. And so you can see the negative because it's 0.5 molar HCl, so it must be 0.5 molar H plus, so negative log of that is 0.3, which is not too bad, 0.62 on the measurement. And you can also do the pH of strong bases, which is basically here, you've only got the qualitative here, which is not that useful. It just tells you it's a base, but doesn't tell the precise number. The measurement tells it's about 12.45, and our calculation is pretty good too, 12.76, I should say. So this time the POH, because this is giving off OHs, so that's negative log of 0.1. And to get the pH, you just take 14 and minus POH, and that's how you get the pH as 13. You can see that they're fairly close, so that's pretty good too. Now moving up to a little bit hard, and in some cases a little bit too hard, which I'll explain in a second. Qualitative, again, doesn't tell you a great deal. This time that we're dealing with weak acids and bases, so there's a certain percentage on the left and certain percentage on the right. You don't know which is which, so you need the Ka values here. They're always less than 1, so this is quite small, 1.8 by 10 to the minus 5. And to do that, you'll learn how to do the Rice diagrams. And this one particular one has some sort of quadratic that's way too hard. You can't get quadratics even in the IB, ITAR or IB. So I just cheated and put it into a math solver calculator to get the value. And then I can do the pH equals negative log, now that I do know the H plus based on the Rice diagrams and the Kas. And so there you go. It is very good. 2.3 measured is 2.49. And so apart from the algebraic equation being a little bit too hard, that is a legitimate year 12 question. They'll probably give you some numbers so that the quadratic can be solved relatively easily. So they can put some x's in there, but not too many that you have to use any sort of complicated math to solve the equation. Okay. And so what's moving up just a little bit harder, and this is perhaps too hard, full stop, is the polyprotics. So as soon as you've got more than one, you have to, you can see the qualitative is not too helpful. It just tells us it's acid, basically. But you have to have a careful look at all the Kas. So the first Ka is strong, so we can just sort of jump straight to that being complete dissociation. And so that one there is a 0.5. And then the next one is up to the -2, so that's now the weak. So we'll do the rice on the weak and we'll carry the 0.5 through. So you can see the rice diagram there. I've put the various numbers in there that are 0.5 and 0.5 at the start, and I'm not sure how much is going to carry through. So I've done the Ka2 there. The equation again is too hard. So in a real question, they probably give you some of these x's, and so that would be solvable. So I've solved that to 0.0115. I need to re-add that to the first equation of H pluses to get through to give me my hydrogen ion concentration. You can see it's pretty good. The equation on the left, unfortunately, is 0.05, but I did put 0.5 in, and I did get 0.2. All right, so I did that one twice, but I don't have the video for that second one. But the measured and calculated values are pretty close. And so that's a good challenge question for you.